Hey everybody. So in this video, we're going to talk about hypothesis testing. So in the last video, last online video, I don't know why my voice just broke. I guess I'm going through puberty again. In the last video, we talked about the sort of foundational aspects or foundational theory that we needed for hypothesis testing. So I encourage you to kind of go back to that and think a little bit about kind of where some of these distributions that we're going to be using in today's video come from. But in terms of practical application, this is kind of where the tire meets the road. I think is the right phrase. In other words, we're going to learn how we actually apply the theory to do something useful. That is hypothesis testing. So with that, let me go ahead and get started. Okay. And let's see, I want to make this large. Sorry about that. Okay. Remember again, we are talking about statistical inference. And so what that is it involves trying to take some data and infer something interesting about the parent populations from which the data are drawn. And we've talked about a couple of different approaches. One was point estimation, which we described in the last couple of videos in a little detail. I'm just going to move straight on to hypothesis testing as the statistical inference we're going to focus on today. And from the last video, basically, we ended up deriving a set of results, and I'm going to kind of summarize those results here because we're going to use them in a bit later. One of the results was that if we form the mean of sample data, say xi, and we're expressing it here as a random variable equation, that the mean itself is a random variable. And the reason is that if you think about how we calculate a mean, basically we go out and collect a bunch of samples and then we compute a sample mean from that. But if we went out and collected another n samples, we would, of course, get different realizations of the value for those samples, and therefore we would have a different sample mean. And we could repeat that 1,000 times, and we would have 1,000 different sample means. And so, therefore, actually, the sample mean is going to be distributed in some way, and therefore it is a random variable. And so we've written the equation for the sample mean as a random variable equation where we have the dependent random variable x bar here as a function of the random variable for the realization of each sample xi, again summed over all the samples and then divided by the number of samples. So that is the random variable equation for the mean. Likewise, we could calculate a sample variance, and for the very same reason, that sample variance is going to be a random variable because every time we go out and collect say n samples, we're going to get some value of the variance. We go out and collect another n samples, we're going to get another variance, and so forth and so on. So our variance, which of course measures spread around the sample mean, our sample variance is also going to be a random variable, which I've indicated here by indicating it in uppercase. Same here. So basically, this is a random variable equation because we're using uppercase. Same thing here. We're expressing the variance as a random variable indicated by the uppercase, and same thing for the sample random variables as well as the mean, the sample means. And one of the things that we concluded when we thought about it in a little detail is that the sample mean as computed by this formula is what we call an unbiased estimate of the population mean, by which we mean if we took the expected value of that equation for the sample mean as, again, a random variable, what we find is that equals the population mean. And go back to the previous video to see how that was done in kind of a step-by-step way. Same thing for the expected value of the sample variance. And in fact, this n-1 here has to be there in order for the expected value of the sample variance to equal the population variance. So you might have wondered where that n-1 came from. You might think if you went back to the definition of variance that it should instead be just 1 over n, like we have here for the mean. The reason it's added is exactly so that the sample variance, when calculated in this way, is an unbiased estimator of the population variance. That is, when we take the expected value of that sample variance, we're going to get the population variance. And we could also say a few things about the probability distribution of the sample mean. And we have essentially two different results. One set of results is for the case where we know the population variance. So maybe we're given it, or we've collected thousands and thousands and thousands of samples over time, so we have a really good handle on what the variance is. But anyway, in this case, we're assuming that we know what, I'm writing it as standard deviation, but of course that's just the square root of the variance. We know the population variance. And in that case, what we found is that basically the probability distribution of the sample means as a random variable is normally distributed with a mean of the population mean and a sort of spread or standard deviation of sigma over square root the number of samples. And I guess the big news there is that as we increase the number of samples, of course, that standard deviation is going to get smaller. And so that means our sample means are going to be more tightly distributed around the population mean as we increase the number of samples. If the sample mean is normally distributed with a mean mu and a standard deviation of sigma over square root n, that means we can construct a standard normal variate, z bar here, which is just going to be the sample mean minus the population mean divided by the standard deviation of the sample mean, or sigma over square root n. And because this is a standard normal variate, we know that it is distributed as a normal distribution with a mean of 0 and a unit standard deviation. Okay, so that's the case when we know the sample mean, well, we know the population variance and we want to know the distribution of the sample mean, so this is what we get. In the event that we do not know the population variance, which is going to be the case for a lot of the problems that we look at, including, for example, the data that you guys have from Huntington Beach, basically, then we need to learn two things. One is the distribution of the sample variance. How is that distributed around the population variance? And what we showed in the last video is that basically the sample variance, indicated here by s squared, when normalized by the population variance and then multiplied by the degrees of freedom, which is the number of samples minus 1, is going to be distributed. That little squiggly thing just means that this thing is distributed, has a probability distribution equal to the chi-squared distribution with n minus 1 degrees of freedom. And so the chi-squared distribution is just another, analytical probability distribution, just like the normal Gaussian distribution or the gamma distribution. But it actually depends on only one parameter, which is the degrees of freedom, that f. And in fact, you can rewrite this result in terms of the degrees of freedom f. And so what we're basically saying is that this quantity here is follows a probability distribution of the chi distribution with f degrees of freedom. And then once we have this result, we can derive from this result a distribution for the sample mean with an unknown population variance. And in that case, if we come back here to remember our standard normal variate, we basically were looking at the sort of deviation of the sample mean around the population mean normalized by this essentially standard deviation of the sample mean. Well, this was the case when we knew the population variance. Now we don't know the population variance, so we construct exactly the same statistic, except we substitute the sample standard deviation, in this case, for the population standard deviation. So we basically replace sigma with s. And this new quantity we call a t statistic, that does the t here. It's a new random variable, and it just represents the distribution of the sample mean around the population mean, and then normalized by this s over square root n. The really key result is that we showed in the last video that this quantity, this new quantity, follows what's called the student t distribution, which is another analytical distribution, which is given by this quantity here. This is the PDF for the student t. And it too is a one parameter distribution. That is, it depends only on the degrees of freedom f. And this symbol here is the gamma, so this is just the gamma function where we're substituting in the degrees of freedom F to get a specific number for that quantity. So that's kind of a summary of what we learned in the last video. And now we want to apply it to hypothesis testing. And kind of let's go back to the big picture. So remember, we've got that population in the wild that we're trying to learn something from. It's going to be characterized, we're assuming that it's a single population characterized by a population mean, mu, and population variance, sigma squared. We take a bunch of observations of that population. We then compute the sample mean and the sample variance. And then we have this question about how accurate the sample mean and sample variance are as estimators of the population mean and population variance. And basically, the summary slide that I just showed kind of provides that information. It tells us kind of both what the expected values are, what the variances are, as well as the distributions. And so with that information, we want to basically then take these x bar and s squared values and use them for hypothesis testing, where we basically want to say, investigate whether maybe the population mean is equal to a specific value or not. And I'll give you a couple different examples of what I'm talking about in a bit. So basically, the hypothesis testing involves, I think, altogether about 6 steps. And we're just going to kind of go through the steps first, and then we'll apply them, and hopefully it'll be clear as we go. So the first step is to define the null and alternative hypotheses. So you can kind of see what we've done there. Basically, in this case, the null hypothesis was that the population mean is equal to some specific value of the mean, mu naught. And the alternative, or H1 hypothesis, is that population mean is not equal to mu naught. So basically, that would be an example of a null and alternative hypothesis. So basically, you can think of a hypothesis more generally as a statement regarding a parameter or parameters of the population, which is tested using samples, experimental measurements of the population. And this is usually done by defining 2 competing hypotheses, just like we did. One of which will be rejected based on the data, and the other will not. So basically, we're going to form 2 hypotheses, and we're going to run some statistical tests that in the end aim to reject one of those 2 alternative hypotheses. And so basically, I've just sort of repeated the set of hypotheses that I had in that previous slide here. The null hypothesis, again, denoted by H sub 0, 0 mean sort of referring to the null, is that the mean is equal to mu naught. And then the alternative hypothesis, where I'm subscripting with A for alternative, is that mu is not equal to mu naught. And again, just emphasize that in these statements, the parameter mu is the population mean, and the parameter mu naught is the specified value of interest. But this is only one type of hypothesis, set of hypotheses you could form. There's lots of different hypotheses you could end up testing. But this is kind of where we're going to start. So that's step 1. We've defined the null and alternative hypotheses. Step 2, we need to identify the proper test statistic and its distribution. And that's going to depend on whether we know the population variance or not. So, and also, of course, the population parameter that is being tested. But we're going to focus specifically on sample means for the moment. So you could be, say, doing hypothesis testing for sample variances or something, but we're going to focus on hypothesis testing for sample means. And again, the test statistic that we focus on for hypothesis testing about the sample means will depend on whether we know or we do not know the population variance. So in the case where we know the population variance, we can go back to that summary slide and realize that our sample mean is going to be distributed around that value that we're hypothesizing the population mean is equal to, that's mu naught, using this sort of standard normal variate, where the standard deviation is going to be the population variance, or standard deviation divided by square root n, where n is the number of samples. And so we know, as we described, that this is a standard normal variate, and so we know it is normally distributed with a mean of 0 and unit standard deviation. So that's the case where we know the population variance. In the situation where we don't know the population variance and we want to understand or do some hypothesis testing about the sample mean, we need to use the t-statistic, because basically in that case, we're substituting the sample, in this case, standard deviation, as for the population standard deviation in that formula. And we know that this t-statistic will have the student's t-distribution. And so instead of it being normally distributed, it's going to have a student's t-distribution. And remember, the student's t-distribution looks like this. This is the PDF form. There are also tables for the student's t-distribution, so we'll talk about that maybe in class. I don't think there's any examples in this particular lecture of that, though. Okay, so we have now completed step 2, where we've identified the proper test statistic. We actually haven't gone through any specific example here, so we just said there are 2 options for the means, either known variance or unknown variance. So then we go to step 3, which is based on a sample of the observed data, we need to estimate the test statistic. Basically, we need to substitute values into it. So for example, in a situation where we know the population variance, maybe we were given that the population variance, or the standard deviation, the population standard deviation was equal to 3. We had 10 samples from the population. We were testing whether the mean is equal to 2, so mu naught is equal to 2, and our sample mean is 5. So that's the scenario. In that case, we would be using the standard normal variate z bar, and we would substitute 5 for x bar, 2 for mu naught, 3 for sigma, and 10 for n. And so when we do that, we get that the actual realization for the standard normal variate in this case is 3.2. Alternatively, if we didn't know the population variance, we would have to use the t-statistic. And so in that case, if we just kind of run with an example, again, these are random numbers. There's no meaning to them. I'm just giving you an example. The mean of 5, again, we're testing whether the population mean is 2. So this is the sample mean. In this case, we have the sample standard deviation is equal to 5. And the number of samples from the population was 10. So we sort of plug and chug, and we get that the realization for that t statistic is 1.9. All right, so we completed step 3. Step 4 is to specify the level of significance. And essentially what this is it's the probability of error that a wrong hypothesis may be selected. So let me try to explain that. So come back to this example. So say we were interested in the null hypothesis that the population mean was equal to some specific value, mu naught, and the alternative hypothesis was just basically everything else, that the population mean was not equal to mu naught. Of course, in the case where we know the population variance, the appropriate test statistic is the standard normal variate. We know that, and we know that it will be distributed follow the normal distribution with a mean of 0 and unit standard deviation. Let's look at what that involves. So basically, we could plot z, our standard normal variate, and then look at the PDF of the standard normal distribution, which you've seen before. And basically, if you think about that, so z bar here is the deviation of our sample mean from the purported or the value of the population mean that we're testing against, right? So that's the mu naught. So we might be interested, for example, is the population mean equal to 5? So we'd substitute a 5 for here. And then z bar would represent the deviation of our sample means from that number 5, given sigma and the number of samples we collected. So you can think of z bar here, the horizontal axis, as essentially being the deviation of our sample mean from 0, which would correspond to a perfect match between the sample mean and the value of the population mean that we're interested in testing against. So 0 would be perfect match, and then of course, if this statistic follows the standard normal distribution, it means that basically there's some probability that this z bar thing is going to be minus infinity, right? The tail goes off to minus infinity. Some probability that it's going to be positive infinity, and there's various probability density all the way in between those two limits. So really what I'm trying to emphasize is that according to this theory, our deviation of the sample mean from the target population mean, mu naught, could be any value, right? That deviation could be anything. And the probability of that deviation follows the standard normal. So it's most likely to kind of occur in this range, but it could definitely occur out in the tail somewhere too. That's what the standard normal distribution is saying to us. So what we would like to say is, look, I mean, we're going to accept the null hypothesis if the z bar that we calculate sort of falls in this range where most of the probability is located. In other words, it's most likely that the z bar, if in fact the population mean was equal to mu naught, it's very likely that z bar would kind of fall in this range where most of the probability density is associated with that standard normal distribution. And then it's less likely that it would fall outside of that range. And so we're going to basically say we'll accept the null hypothesis if it falls in this range, and we'll reject if it falls outside of that range, because there's relatively little probability that we would get a z bar value out there, even though it is possible, it is probable. And so, okay, so that's kind of the setup. But then the question is, where do we set these thresholds between where we accept the null hypothesis and where we reject it? And the answer to that, it's really kind of a cool answer, is that we basically specify the probability we are willing to accept of being wrong. Because the fact is, there is some probability out in the tails that our z-bar would be, a realization of that z-bar would be out here. And that the sample mean then would deviate from the population mean, equal to mu naught, sort of out in this range. Let me see if I can try to rephrase that. So in the event that the population mean is equal to mu naught, and so our null hypothesis is actually correct, there is still some probability that z-bar, we're going to get a realization of z-bar, which is out in the tails. So we basically have to say, okay, what probability are we willing to accept that we will reject the null hypothesis? In other words, we'll accept the alternative hypothesis when in fact the null hypothesis was correct, which is represented basically by this probability distribution here in blue. And so we're really talking about then taking whatever that probability is and say we set that probability threshold to 0.1. So we're willing to accept a 10% probability of being wrong. And so that means that basically we're willing to accept the possibility that z-bar is going to fall into this upper 5% of the tail or the lower 5% of the tail. And then we need to calculate what the corresponding critical z-bar values would be for that. And in order to do that, we just go to our table. So if you think about setting alpha equal to 0.1 and then dividing half of that probability of error into sort of an upper tail and lower tail, we're really talking about, for this particular value here, a cumulative probability of 95%. So we just go down here to a cumulative probability of 95%. It's going to be somewhere between 1.64 and 1.65 for critical value. And in fact, that's exactly right. It's 1.645. And so this value here is just going to be, because the PDF is symmetrical, it's going to be minus 1.645. And so basically then what we're saying is, in this scenario, if we are willing to live with a 10% probability of calling it wrong, that is, that the null hypothesis is actually correct, but we're going to reject it, then we will define the critical value of z-bar as plus or minus 1.645. And so any z-score values that we calculate from our sample mean that either exceed 1.645 or fall below minus 1.645, we're going to reject the null hypothesis, even though we know that it might be correct. Okay, so hopefully that makes some sense. And then in step 5, we need to define the region for the null hypothesis. And so like in this example here, basically, you notice it's basically, we'll reject the null hypothesis if our z-bar value falls in either the sort of tail to the left or the tail to the right. And so we basically need to decide whether, in fact, we're looking at a two-tailed test or a one-tailed test, and I'll explain what I mean by that. But that's step 5, basically, is defining the region of rejection, which involves deciding if the test is one-sided or two-sided. So let me explain that. Like Hamlet might have said, one-sided or two-sided? That is the question. I know that's a bad joke. So when we are comparing the population mean to a specified value, it is possible that we may only care if the population mean is greater than or less than a specified value. In such cases, we perform a one-sided test because we need to check if the population mean is only greater than or less than the specified value. If we want to know if the population mean is different than the specified value, we perform a two-sided test because we need to check if the population mean is greater than or less than the specified value. So that's a bunch of words, may not make any sense, but it's actually quite simple. Let's go through it. So for a two-sided test, basically it's exactly like what we just described in the kind of example that we went through. That is, our null hypothesis is, for example, that the population mean is equal to some specific value mu naught. And the alternative hypothesis is that that population mean is not equal to that mu naught. Well, that could happen if we kind of go way back to this point. That could happen if basically the z-bar value is too large or if the z-bar value is too small, and that's why this would correspond to a two-sided test. A one-sided test, on the other hand, look like this. Say we again have the null hypothesis that the population mean is equal to mu naught. The alternative hypothesis is that the population mean is greater than mu naught. So we really only care in terms of rejecting the null hypothesis if mu is greater than mu naught. Alternatively, we could have a case where we will reject the null hypothesis if mu is less than mu naught. These would both be examples of one-sided tests. And so once we've decided on the region of rejection, we essentially compute the critical value. We already kind of went through that a few minutes ago of the test statistic. And then we look at how it compares with the actual value of the test statistic we calculated from our sample mean. All right, so let's kind of go through the whole thing and with a couple of examples, because I think this is a case where seeing it in practice really makes a huge difference. So this is actually kind of based on a true story, as I was saying in class. The name has been changed to protect the innocent. But Joe conducts 5 Flume experiments, and in each of these experiments, he measures a parameter we're going to call W. The parameter's name has also been changed to protect its innocence. From these 5 measurements of W, he computes a mean of 1.2. Joe concludes, quote, "Because the mean of my measurements is greater than 1, my experiments demonstrate that W is greater than 1. And so then the question is he correct about that assessment? And so let's kind of go through the steps we just outlined and apply them to Joe's example. So the first thing that we need to do is define the null and alternative hypotheses. And basically, we could imagine doing this as either a one-tailed test or a two-tailed test. So in the case of one-tailed test, basically what we're saying is that the null hypothesis is that W equals 1. And if you look back at his statement, basically he's rejecting that null hypothesis by saying that W is greater than 1. So anyway, that would be the null hypothesis. And the alternative hypothesis would be that W is greater than 1. So we would basically then reject the null hypothesis if we had evidence that W was greater than 1. And so basically by formulating the hypotheses in this way, we can say that in his statement, Joe is essentially rejecting the null hypothesis. If you go back to his statement, he's saying that because the mean of his values is 1.2 and that's greater than 1, therefore his experiments demonstrate that W is greater than 1. And so that would be essentially rejecting the null hypothesis and accepting the alternative hypothesis. So the alternative example might be just like alternative facts, right? The alternative example might be a situation where he says, because the mean of my measurements is greater than 1, my experiments demonstrate that W is not equal to 1. So it's a slightly different kind of statement. And in that case, basically, it's a two-tailed test because we will reject the null hypothesis if either W is greater than 1 or W is less than 1. Okay, and so by formulating the hypotheses in this way, I should say hypothesis, Joe is still rejecting the null hypothesis. He's saying that W is not equal to 1. But in this case, we recognize there may be 3 possible outcomes. W is equal to 1, less than 1, or greater than 1. Okay, so we've defined the null and alternative hypotheses. We need to identify the proper test statistic and its distribution. And so we're talking about means here because he's saying that the mean is greater than 1. So basically we have 2 different possible test statistics for the mean. We have one with known population variance and one with unknown population variance. And you may remember this is what we had for the known population variance. It's just the standard variate, which is going to be distributed according to standard normal. And in the case of an unknown variance, we have the t statistic, which is going to be distributed according to the student's t distribution. Based on the sample of observed data, we need to estimate the test statistic. And so for the moment, let's assume that the standard deviation is known, the population variance and standard deviation is known, and equal to, in this case, 1.5. So sigma is going to be 1.5. Then the test statistic is the standard normal variate. So we choose that because we know the population variance, in which case we write z bar out as x bar minus mu naught, which is our target mean that he's comparing to, divided by the standard deviation of x bar, sigma over square root n. And so in that case, you remember his mean was 1.2. We're comparing to a target mean of 1, trying to see if 1.2 is different than 1. And we're dividing by the known sample standard or population standard deviation, 1.5, and dividing that by the square root of the number of samples he collected, which is 5. So in this case, his test statistic works out to 0.298. So we've done step 3. Next thing we needed to do is specify the level of significance. And this is essentially, again, the probability of error that a wrong hypothesis may be selected. So we need to then go, we need to maybe dig a little bit deeper into what we mean by an error. And really, there's 2 different ways we could kind of screw up, right? And these are called type 1 and type 2 errors. So if we reject the null hypothesis, we are saying that the population mean for W does not equal to 1, but we could be wrong. And when we reject the null hypothesis, or if we reject the null hypothesis, when in fact it is correct, that would be a type 1 error. So here's kind of a table to help you understand the relationship between type 1 and type 2 errors. So say that the truth about the population is that the null hypothesis is true, but because of randomness in our sampling of that population, or maybe we don't have enough data, we end up rejecting H0 with some specified probability. That, because we've rejected H0 when in fact it was true, that's called a type 1 error. Alternatively, it could be that the null hypothesis is not true, which means the alternative hypothesis is true, but that we accepted the null hypothesis, again, because of randomness in our test statistic, and that would be a type 2 error. So basically, these are 2 different types of errors. When we specify the probability of accepting an error, usually we're specifying, the typical approach is to specify the type 1 error. So we're specifying the probability that we reject the null hypothesis when in fact it's true. Okay, and then we need to define the region of rejection for the null hypothesis, which really comes back to whether the test is one-sided or two-sided. So kind of let's think about the situation where we accept a probability of type 1 error, which is essentially called alpha, equal to 0.05. So 5% chance that we're going to have a type 1 error, which is going to be essentially the case where our test statistic ends up giving us a value out in this upper tail somewhere. This is a one-sided test because remember in the case of example 1, we were interested in evaluating the possibility that W is greater than 1, in which case, the null hypothesis is W equal to 1, and the alternative hypothesis is that W is greater than 1. In that case, W equal to 1 is going to be represented by all this kind of light blue probability. So if our z-score falls anywhere in this range, we would accept the null hypothesis. But if it falls beyond 1.645 into this probability region where we are willing to reject the null hypothesis, even though it might be correct, we're going to call that the rejection range. So this would be an example of the one-sided test. In the case of the two-sided test, if we still stick to the alpha equal to 0.05, so we're willing to accept a 5% probability of committing a type 1 error, that 5% probability has to be divided between the upper and lower tail. So basically, the light blue probability indicates the sort of region where we're going to accept the null hypothesis. And then if our z statistic falls into the upper or lower tails, sort of where there's a dark blue region, we're going to reject that. And remember, this probability distribution, again, is for the case where essentially the null hypothesis is correct. So all of this is the probability we're going to get a particular z-score given that the null hypothesis is correct. There's a certain probability that z-score is going to be out here. We're accepting the probability of that, of getting the wrong answer, and that's why we're setting that alpha equal to 0.05. So in this case, we've got essentially 2.5. We have to divide that 0.05 into upper and lower tail. So we've got 2.5% of the probability in the upper tail and 2.5% of the probability in the lower tail. And that means we need to find the corresponding critical statistic value for those two regions. And you can see, obviously, it's 1.96. Where does that number come from? Well, in the case where we divide this 0.05 between upper and lower tails, that means that we're looking at 2.5% of the probability out in this region here, which means that up to this point, we essentially have 97.5% of the probability. In other words, if you integrate it up, the PDF up to this point, we would have 97.5% of the probability. And so we need to go to 97.5, which is going to be around here. And yes, lo and behold, that corresponds to a critical z-bar statistic of about 1.96. So that's where this number comes from. So basically then, depending on whether we have a one-sided test, where we're basically just rejecting the null hypothesis if W is greater than 1, or a two-sided test where we're rejecting the null hypothesis if W is greater than or less than 1, we're going to get different critical values for the z statistic. All right, and then we finally compare the critical and test statistic values to determine whether we're going to reject or not reject the null hypothesis. And what that is, it's the simple part. We already calculated the measured z statistic at 0.298. Remember, let's kind of go back, way back. Sorry, oh, there it goes. So remember, we basically substituted values for the mean that he calculated, the target value for mu naught, the standard deviation of the population, 1.5, and the number of samples, and we got 0.298 for that realization of the z statistic. So we now go back down. Okay, so basically our measured z statistic is 0.298. Recall that we determined that for the one-sided test, our critical value for the z statistic is 1.645. So if the measured z statistic falls above 1.645, we would be in the rejection range. But if you compare these, obviously we're not. The ZM equal to 0.298 is well within the acceptance range of our null hypothesis. And so we conclude that the null hypothesis cannot be rejected. And so basically what that implies is that he's correct, that W equals 1 at a statistical threshold of alpha equal to 0.05. So now we've just completed our first hypothesis test. Congratulations. Now, alternatively, we could have done the two-sided test, and basically the idea there is we're going to reject the null hypothesis if either W is greater than 1 or W is less than 1. So we have to divide that 5% probability into both the upper and lower tails of our standard normal distribution. And so our null hypothesis, again, is that W equals 1. The alternative is that W is not equal to 1. That is, it could be either greater than 1 or less than 1. And we're still adopting that 5% threshold of committing a type 1 error. Remember, type 1 error is when you reject the null hypothesis when in fact it's true. And so basically, if we already did this, we basically found that the cumulative probability is represented by the standard normal distribution equal to 0.975 occurs when the critical value is 1.96. And then, of course, by symmetry, we know on the lower end that's got to be minus 1.96 because this PDF is perfectly symmetrical. And so we again compare our sort of measured Z statistic to the critical values greater than 1.96 or less than minus 1.96. And we find that our critical value still falls within the accept of the null hypothesis. And so we conclude that the null hypothesis cannot be rejected for this two-tailed test either, and that W equals 1 at a statistical threshold of alpha equal to 0.05. All right, so that was your first sort of application of hypothesis testing. Let's go through another example. This is example 6.3 in the textbook. Suppose the specification for the yield strength of rebars required a mean value of 38 pounds per square inch. It is therefore essential that the population of rebars to be used in the construction of a reinforced concrete structure has the required mean strength. From the rebars delivered to the construction site by the supplier, the engineer ordered that a sample of 25 rebars be randomly selected and tested for yield strengths. The sample mean from the 25 tests is 37.5 psi, and you can see that 37.5 psi is less than 38, if you just compare the two numbers, right? But the real question is that statistically significant or not? It is known that the standard deviation of rebar strength from the supplier's 3.0 psi, so we're given the population standard deviation. And then the question is, should this lot be rejected? So you are going to cost the supplier a lot of money if you reject the lot. So you better get this right. And so the right way to do it is through a statistical hypothesis test. So there's our tests or our steps again. This is the last one to compare the critical and calculated statistic, but same idea. So let's go through the steps applied here. So basically, we have a one-sided test that's going to apply. And the reason is that our null hypothesis was really that the population mean is greater than or equal to 38. Now, it's worth talking about that for a second because that problem statement didn't exactly say that, right? They basically said that if you come back to the problem statement, that the yield strength of rebars required a mean value of 38 psi. But the point is, if the rebars were stronger than 38 psi, we'd have no problem with that. That'd be perfectly fine. The only thing we do not want is that the rebars have a strength of less than 38 psi. So our null hypothesis is going to be that the rebar strength is greater than or equal to 38. So that would be a case where we would not reject the lot. The alternative hypothesis is that the population mean is less than 38, in which case we are going to reject the lot. This is going to be a one-tail test. Next, we need to identify the proper test statistic and its distribution. And in this case, we know we're basically working with the mean, right? So we're going to use a statistic from the mean. And furthermore, we know the population variance and standard deviation, and so we're going to use the standard normal or Z statistic, which we know is distributed according to the standard normal. And then step 3 is we evaluate that test statistic. So we're going to plug in the mean of those, I think, 25 rebar tests, which was 37.5. The comparison, the sort of target mean that we're comparing to, which is 38. Our known standard deviation from the population, which is 3, and the number of samples, which is 25. And that works out to minus 0.833. So that's essentially the measured, this should be Z actually, probably, it doesn't really matter, but this is a Z statistic, not a T statistic. So this is our measured Z statistic. And then we need to specify the level of significance of a type 1 error. Remember, type 1 error, is the case where we reject the null hypothesis even though it's true. And we're just going to select, look, I mean, typically you either choose alpha equal to 0.1 or 0.05. Here we're going to be more conservative and take only a 5% probability of being wrong. So we're going to set alpha equal to 0.05. And so basically, in that case, the one-tailed test is going to look like this. If the, if we come back to this original statement, so the null hypothesis we're going to accept if the null hypothesis is that the mean of the rebar is greater than 38, the strength is greater than 38. The alternative is that it's less. So if we come to this plot here, basically that translates with a 5% probability of a type 1 error to the Z-score being essentially greater than minus 1.645. We accept the null hypothesis. If it's less than minus 1.645, so our rebar strength is essentially getting much less than the 38, then we're going to accept the alternative hypothesis, which means we reject the null hypothesis and send the lot back. And so we know this minus 1.645 comes from essentially allowing 5% of the probability in the tail here to be our rejection, our type 1 error associated with rejecting the null hypothesis. And so we would just, we've already talked about this, but again, that 1.65 comes from essentially saying that we're going to accept a 5% probability of being wrong. Remember, this table only is true for, or only valid for positive values of the critical or Z-bar. And so if we, but it's totally symmetrical, so we can come up to 95%, pull out a 1.65, and then the corresponding value for the 5% probability in the left tail is going to be minus 1.645. Okay, so we calculated that Z statistic at minus 0.833. We have the critical value equal to minus 1.645. And so now we just compare those two, and we can see that our calculated value or measured value of the Z statistic falls within the region where we're going to accept the null hypothesis. So that implies that in this example, the rebar satisfies the required strength. So we would not reject the lot. So that's pretty much all I had to share with you for this particular lecture. I hope that it was clear and that you enjoyed. And I'll see you in class tomorrow. Okay, bye.